Having understood why and where an electrochemical reaction occurs from last two lectures, we next look into the rate of electron transfer and how the theories are rationalized. To that end, we here introduce several key theories established by the giants in the field of fundamental electrochemistry, and theories are in sequence: Faraday's law of electrolysis, Butler-Volmer kinetics, Tafel plot or Tafel relation, and the last is marker theory. Although we have learned it from the early age of high school, it's always important to recall the Faraday's law of electrolysis when it comes to fundamental electrochemistry. Any electrochemical reaction is in essence the conversion between chemical energy and electrical energy, and the quantification law behind that was discovered and summarized by the great scientist Michael Faraday in 1833, who also invented the terminology electrode. And the quotation below is his original statement of the law. Here, the chemical power of a current of electricity refers to the mass of the consumed electroactive species, and the absolute quantity of electricity which passes means the charge we measured during the electrolysis. So mathematically, we have the mass equal to the molar mass of the electroactive species divided by the product of the charge number of the species and the Faraday constant. And further, we have charge equal to the integral of current with respect to time, which also equals to the amount of the electroactive species times Z and F, and therefore we have the amount of species equal to 1 over ZF times the integral of the current with respect to time. From the Faraday law of electrolysis, we know that the integral of current with respect to time is proportional to the amount of materials consumed during the reaction. And next, it's even more important to know the quantitative relation between current and electrode potentials applied. Another great scientist, Tafel, in 1905, discovered an empirical relation between current and electrode potentials, and it shows not a simply ohmic relation, but a logarithmic dependence of current on the electrode potentials applied. And this shows the great sensitivity of current to the potentials applied. A small electrode potential change can induce the changes in the order of magnitude of current. This interesting quantitative relation was later on rationalized by a combination of several key fundamental theories. The first to emphasize is the dynamic nature of equilibrium. As mentioned in the very first section, equilibrium state does not mean there's no molecules reacting, but instead the rate of the forward process and the backward process equals to each other. Consider again the following process: O plus E in equilibrium with R, and the rate of the forward cathodic process is denoted as Kc, and that of the backward anodic process is denoted as Ka. The rate law tells us the net reaction flux equals to Kc times concentration of O minus Ka times concentration of R. And the amount of materials reacted at a uniformly accessible electrode surface is equal to Ja, the electrode area, times T, the reaction time. And we also have the derived Faraday law: the charge equals to N times F, with Z, the electron transfer number, equals to 1 for the process above. Combining these three equations, we have Q divided by T equals to the current, which is F times A times basically J. Then at equilibrium, we have current equals to 0. So readily we have Kc divided by Ka equals to the concentration ratio of R to O. And because at equilibrium there's no net conversion rate, so we can define Kc divided by Ka equals to the equilibrium constant, which further leads to the equity. Therefore, we see that the kinetic theory predicts a constant concentration ratio, which is exactly what thermodynamics does. So this in turn confirms the dynamic nature of equilibrium. And importantly, from the derived equation in this bit, we learned the quantitative relation between current and rate constant of each elementary process. Next, it's important to further explore the rate constant by Eyring equation. Eyring equation has a very similar form to that of Arrhenius equation, but is developed for condensed phase matters. And it writes as the rate constant equals to AF times e to the power of minus delta G double dagger divided by RT. Delta G double dagger here means the standard Gibbs energy of activation, R is the gas constant, T is the temperature. While the whole exponential term may reflect the probability of molecules going over an activation energy barrier, the AF can be understood accordingly as the frequency factor of molecules attempting to climb over the energy barrier. Then it's important to further specify what the standard Gibbs energy of activation means. We need to look at the Gibbs energy curve again. The standard Gibbs energy as a function of reaction coordinates. And the Gibbs energy are plotted separately for the reactants and the products. And they meet at the crossover point, which is the assumed well-defined transition state. It should be noted that here we discuss the Gibbs energy only at the standard state, because Gibbs energy is concentration dependent, whereas in the Eyring equation, the rate constant is not concentration dependent, especially in dilute systems. So the theory I'm going to present in the following needs to be in the context of the standard state of concentrations. And in the Eyring equation I wrote, I omitted the usual superscript O for denoting the standard state, just for convenience. And the reaction coordinates actually refers to a particular structural parameter of reactive species, for example a bond length or angle. Most reactant and product molecules are considered to stay at the minimum of their energy distribution curves. As the reaction proceeds, the reactant molecules may do thermal motion so that their structures will be distorted, along with the rise in their energies. And when it reaches the transition state, which means the molecules now has a transitional molecular geometry in between reactant molecules and product molecules. As such, the energy required for this process, or the difference between the energy maximum and minimum, is the standard Gibbs energy of activation. As such, we have further understood the quantitative relation between rate constant and the standard Gibbs energy of activation, and also the physical interpretation of the latter. Now it comes to the core part of the kinetic theory, the most successful and widely accepted Butler-Volmer model of electrode kinetics. Consider again the same one-electron transfer equilibrium, with Kc as the rate constant for the forward process and Ka for the backward process. Then we need to look at the standard Gibbs energy curve as a function of reaction coordinate. We start with the lower standard Gibbs energy curve of reactants, where the electrode is at the standard electrode potential, and then we polarize the electrode to a more negative value. So for the Gibbs energy of reactants, according to the electrochemical potential introduced in the very first section, it equals to ZF phi S minus phi m times F plus mu O plus mu E. From this equation we can see that if we make phi m more negative while all the other terms are constant, then the change in the Gibbs energy of reactants must be positive, and it equals to minus F times E minus E naught. But the key consequence of this electrode polarization is the shift in the reactant coordinate of the transition state. As a result, the change in the Gibbs energy of activation is not the same as that in the Gibbs energy of the reactants, but rather a fraction of it. To better formulate and simplify the change, we approximate the energy curves around the crossover points to the orange straight lines, and the fraction of the change is denoted as alpha. So we have the new standard Gibbs energy change of activation for the reduction equal to the initial value minus alpha F times the potential difference. And similarly for the oxidation, we have this equality, where for sure alpha should be bigger than 0, smaller than 1, and is actually called transfer coefficient, which is understood as a measure of symmetry of the energy barrier. And conventionally, we define the transfer coefficient for the reverse process, the oxidation, as beta equals 1 minus alpha for the simple 1 electron transfer process. Then we substitute the two equations above into Eyring equation. So we would have Kc equals to AC times e to the power of minus this divided by RT. Similarly, for the oxidation, we have AA times e to the power of minus this divided by RT. Then we consider a special case where constantly at the standard state, the equilibrium constant of the reaction equals to 1, such that we would have Kc equals to Ka at equilibrium. So in this case, at the standard state, the forward reaction and the backward reaction had the same values of the rate constant. So we formally define the rate constant as the standard electrochemical rate constant, denoted as K0. And apparently we have the electrode potential as the standard one. And at equilibrium, there shouldn't be any difference between the standard Gibbs energy of activation for the forward and for the backward process. Then combining the three equations with the two equations above, we would have the standard electrochemical rate constant equal to the former part of Kc and equals to the former part of Ka. And since for an elementary process the rate constant is always fixed in a given temperature and pressure and does not depend on the concentration of O or R, so these are general expressions. In combining all these new results with the rate law, we would have current equal to F times A times K0 times brackets e to the power of minus alpha F times the potential difference divided by RT times concentration of O minus e to the power of beta F times potential difference divided by RT times concentration of R. And this is the famous Butler-Volmer equation. So this is of tremendous practical use because it directly relates current to the electrode potentials applied and to the surface concentration of the electroactive species. So from this bit we are able to derive the quantitative relation between the Gibbs energy of activation and electrode potentials applied. Then along with the first and the second bit, we are able to derive the current potential relationship. Using the established Butler-Volmer equation, we can now derive the empirical Tafel relation. For the same process, and this time we consider its low electrokinetics, or with a small k0. And when the rate of the overall reaction is dominated by the interfacial electron transfer rather than mass transport, which will be introduced as shown later in Lecture 5, we would have the electrode potential applied smaller than the standard formal potential, and mathematically this can lead to the negative potential difference is bigger than itself, such that we can have a further inequality with a bigger difference in the values. And then if we assume the transfer coefficient for the forward and backward processes are very similar, we can omit the second term in the Butler-Volmer equation, so that we have reduction current is approximately Fa 0 e to the power of alpha f, the potential difference, divided by RT times the concentration of O. And rearrangement would give us the overpotential, or the potential difference, equals to minus RT divided by alpha f times ln the absolute value of reduction current plus C, where the constant equals to RT divided by alpha f times ln Fa K0 concentration O. So from the derived equation above, we can see the linearity between electrode potentials applied and logarithm of current. And apparently this is subject to the condition where the concentration of O stays constant, which means when the mass transport is not important. In practice, we often use the Tafel equation to attain the fundamental kinetic parameters, the transfer coefficients alpha and beta. Simply by rearrangement, we would have the logarithm of current equal to minus alpha f divided by RT times the electrode potential plus another constant. Similarly, for the oxidation, we would have this equality, and we can further plot the natural logarithm of the absolute value of the current as a function of the electrode potentials applied. Assume the standard formal potential is here. For the reduction, we may have this straight line plotted with a slope of minus alpha f divided by RT. And similarly, for the oxidation, the slope will be beta f divided by RT. So from the slope we can get the value of alpha or beta, and for this one electron transfer process the value is in between 0 and 1. And take alpha for example. If alpha equals to 0.5, then it means the energy barrier is symmetric. So the molecular geometry of the transition state resembles neither that of the reactants nor that of the product molecules. And if alpha is more than 0.5, then the energy barrier is asymmetric. So the transition state is product-like. And conversely, for a value bigger than 0.5 is still asymmetric, but is reactant-like. And for this case, it means it would be relatively easy for the reactant molecules to reach the transition state, implying the ease of the electron transfer. So the value of the transfer coefficients, which can be derived from the Tafel plot, can provide insights into the reaction mechanism. Therefore, a Tafel plot is a very important analysis in practice in the field of fundamental electrochemistry.